We'll try our algorithm on several other problems to check its accuracy and to see if we can do integer numbers, decimal fractions, and mixed numbers. From 12,250, I'm going to subtract 5,375. I'm going to use the textbook algorithm first, and then we're going to use Nine's complement procedure, and then we can compare the two procedures. 5 is greater than 0, so I have to borrow 1 from this 5, that becomes a 4. So 1, oh, this becomes a 10 now. 7 is greater than 4, so I have to borrow 1 from this. That becomes a 1. 2 becomes 1, and this becomes 14. 3 is greater than 1, so I have to borrow 1 from this 2. That becomes a 1, and this becomes an 11. 5 is greater than 1, so I have to borrow 1 from this, 1. That becomes a 0, and this becomes an 11. So I have to modify my minuend extensively in order to do the subtraction by subtraction, the textbook algorithm. The number transformations that were necessary: 1, 2, 3, 4, 5, 6, 7, 8. Now I'll do the subtractions. 5 from 10 is 5. 7 from 14 is 7. 3 from 11 is 8. 5 from 11 is 6. 0 from 0 is 0. So my difference is 6,875. How many operations did I do? 8 number transformations of the minuend. Then 4 hard subtractions. 5 from 10, 7 from 14, 3 from 11, 5 from 11. So I did 12 operations in order to get this difference, 6,875. All right, now we'll do it by the Nine's complement procedure. I'm going to rewrite the minuend without modification. We are not going to modify the minuend whatsoever. If the subtrahend digits are less than the minuend digits, which they are, then I have to add a leading 0. I have to add as many leading zeros as I need to make the subtrahend digits equal to the minuend digits. This is 4 versus 5, so I add the 0. The 0 is necessary because I must take the Nine's complement of the subtrahend. What number added to 0 gives you 9? 9. What number added to 5 gives you 9? 4. What number added to 3 will equal 9? 6. What number added to 7 that will equal 9? 2. And what number added to 5 that will equal 9? 4. Now that I have the Nine's complement of the subtrahend, I proceed to add. 4 and 0 is 4. 2 and 5 is 7. 6 and 2 is 8. 4 and 2 is 6. 9 and 1 is 10. Now we notice something about this difference, 6.875. These 4 digits are almost equal to it. So the last step in the Nine's complement procedure is to take this 1, this leftmost digit 1, and add it to the rightmost digit, 4 in this case, and I get 6,875, 6,875. I get the correct difference. Where did this extra 1 come from? In subtraction by subtraction, we start with the minuend and then we subtract a number from it. So we're going to get a smaller number. In subtraction by addition, we are adding 94,624 to the minuend. Consequently, there's going to be a carryover in the 10,000s place. That leftmost digit will always be a 1 in the Nine's complement procedure, and add it to the rightmost digit, and you get the correct difference. And we did it by addition. We had to convert the subtrahend to its Nine's complement and then we did 5 simple additions. This is much easier than the textbook algorithm for subtraction by subtraction. Subtraction by addition is much easier for a simple fundamental reason that addition is easier to do than subtraction. There are no borrowings, and we don't have to modify the minuend at all. In our next problem, we'll test the algorithm, the 9's complement procedure, for a mixed number. We want to subtract a mixed number. Here's our original problem. 12 point, as a decimal fraction, 12.250 translates into 12 1/4. 5.375 translates into 5 3/8. So I want to subtract 12 from 12 1/4. I want to subtract 5 3/8, and what I should get is 6 7/8, 6.875. I want to do it, of course, by the 9's complement procedure, so I have to find the 9's complement of 5 3/8. So what I'll do is add a 3 to that 5. 5 and 3 is 8. 3/8. To make 8/8, I need 5/8. So 3 and 5 is 8/8. Now, when you add those two numbers, 8 and 8/8, that's equal, that's another way of writing 9. So this number, 3 and 5/8, is the 9's complement of the subtrahend, 5 3/8. Now I'm going to proceed to add. But first I must convert this 1/4 to eighths. So I'm going to multiply by 1. And then I'm going to substitute 2 over 2 for 1. So I get 2 times 1 is 2, and 2 times 4 is 8. So 2/8 is another way of writing 1/4, 1 over 4. So now I'm going to add 12 and 3 is 15. 2 and 5 is 7, and I'll bring the eighths over. So I get 15 7/8. Now my last step in the 9's complement procedure is to take that 1 and leftmost digit 1 and add it to the rightmost digit. And when I do that, I get 6 7/8. So 12 1/4 minus 5 3/8 equals 6 7/8, which is what I have here when you put the decimal points in, 6.875. The algorithm is valid for all numbers. Integer subtraction, decimal fraction, fractions, and mixed numbers. So it's valid for all numbers. The special case that we learned in CLIP 1 and CLIP 2 will allow a student in the first grade who is learning addition for the first time, when they reach the level of skill where they can add two basic numbers that sum to 9, they can be taught to do subtraction by addition. And they can verify. They don't have to memorize the facts in the subtraction table. They can verify it using the special case algorithm. And the general case algorithm is valid for all numbers. And where did it come from? This handheld calculator, and every handheld calculator on the planet, and every computer on the planet does subtraction by addition and has done it that way since their inception. And we can turn the special case into the general case. What we have to do is look at the digits in the subtrahend and make sure that they're equal to the digits in the minuend. So we have to add leading zeros, as many as you need in order to make the two numbers subtrahend minuend equal, because you must take the 9's complement of zeros in order to get the 9's complement procedure to work properly. Otherwise it will fail. What method should be taught in elementary school? Both. Textbook algorithm and subtraction by addition using the 9's complement procedure.